Hello everyone. Let's continue chapter 1 by discussing the network core. In the network core, we are going to talk about packet and circuit switching and as well as the internet structure. Now at the network core, we have a mesh of interconnected routers. And in the picture, we are seeing the local and regional ISPs, and we are seeing national or global ISPs. And as you can see, there are a number of interconnected routers in these ISPs. The network core performs an important function called packet switching. If you remember from our previous lecture, hosts or end systems break application layer messages into packets. And the network forwards packets from one router to the next across links on path from source to destination. Let's say you are at your home, at your house, and then you want to connect to the Amazon website, and then your browser will send the message, will break the message into packets, and then they'll send the message to the edge router, which will be forwarded to the local or regional ISPs. And let's say the Amazon website resides in this data center, and these routers will forward these packets into this data center, and the Amazon website web server will send back the Amazon website to you. And there are two key network core functions, and we have a network of routers in the picture we are seeing. Now, each of these routers has two core functions, and one is called the routing and the other is called forwarding. And these routers has a local forwarding table which includes a header value and output link. Now, forwarding is also called switching, and this occurs locally, so the router moves arriving packets from router's input link to the appropriate router output link. Let's say this is the packet that our browser breaks into smaller chunks, and then this packet will be forwarded to the Amazon web server, and this packet consists of the destination address. Here this is 0111, and when we look at the table, we are going to see that this header value corresponds to the output link 2. So this is the arriving link, and this is the outgoing link. So this router will forward this packet based on its destination address to its outgoing link, such as the second output link. And now this packet has to move toward the Amazon web server, so it's forwarded to this router. And each of these routers has also the routing mechanism, has a routing algorithm. Normally, in most cases, the routing algorithm has also what we call the routing table. And based on the routing table and the routing algorithm, this router knows that it's going to forward this packet to this router, and then the packet will be moving toward the Amazon web server. And the routing is actually a global action in which the router determines source and destination paths taken by packets, and this is called routing. And let's see an example to understand the concept in a clear way. And let's assume that we are going to drive from San Jose to the Northampton. We are going to drive from the West Coast to the East Coast. And this is routing. So we are going to start from San Jose, and we are going to reach certain destinations along the way. And for example, we are going to reach Iowa. We are going to pass from Chicago, and we are going to pass from New York, and we are going to arrive at Northampton. So this is called routing. And in San Jose, we have multiple roads going in and out. So the road that we are going to take is determined by the switching function. So, or let's say forwarding function, and then along the way we may reach to Cleveland, and again a similar function occurs here, such as that there are incoming links and outgoing links, and we are going to determine which route to take. So we are going to arrive at a certain link, and then we are going to depart, or we're going to transport from an outer link, which will move us closer to the Northampton. And this is called forwarding. Store and forward is an important function of packet switching. Now we have our application such as a web browser, and then this web browser, this networking application, will divide our message into packets. In this example, we have 3 packets, and the first packet is being sent over the link to the next router. And as you can see, the bits are being sent over the link, and here this is storing the bits for that packet. Now, when this occurs, we have a packet transmission delay. So it takes L over R seconds to transmit or push out L bit packet into the link at R bps, so R bit per second. So here's one hop numerical example. Let's say that our packet consists of 10 kilobits, and then the transmission rate is 100 megabits per second. So the one hop transmission delay becomes 0.1 millisecond. Now in store and forward, the entire packet must arrive at the router before it can be transmitted onto the next link. So in this example, the router will wait until all bits in the packet arrives at this router, and when the packet is complete, then it will be forwarded. And that's why it's called store and forward. Now there's another mechanism in packet switching networks called queuing. Now we have A and B. These are 2 hosts, and they are sending packets to the router, let's say to the edge router, and this is the packet coming from A, and this is the packet coming from B, and the packets coming from A are marked with green, the packets coming from B are marked by blue, and the link rate, the R, is 100 megabits per second in this link, but the link between this router and the other router is slower. The capacity is slower than this link over here. So R is 1.5 megabits per second. And of course, let's say that from A, we want to send packets to, let's say, C. So the packets are following this path to the host C. Now, queue occurs when work arrives faster than it can be served, right? So here we have a faster link, and here we have a slower link. So in order this packet to be sent, it has to be sent completely, but since this is slower than this link, then these packets will be queued in this router. So here are examples, for example, and here we have cars, we have people, and we have passengers waiting for the bus. Now the bus capacity is less than the number of people waiting, so there's the queue. So when we look at the packet queuing and loss, if the arrival rate to link exceeds the transmission rate of link for some period of time, now the packets will queue waiting to be transmitted on the output link, and packets can be dropped or lost if the memory buffer in a router fills up. So here, since this is a slower link than this one, eventually this queue, the memory buffer will be full, and since this router will try to forward all packets, the new arriving packets will not find a place in the memory, so they will be dropped, or basically this is lost. and this is how the messages are lost or how the packets are lost in networking, because the buffers are full and the routers do not have a room for new packets that are arriving. The alternative to packet switching is circuit switching. Now, let's say we have host A and we have host B, and let's assume that these are having a video chat through these lines over here. Now, in circuit switching, end-to-end resources are allocated, and these are reserved for call between source and destination. And we are going to talk about why it's called a call in this particular case. And in diagram, each link has 4 circuits. If you count here 1, 2, 3, and 4, and call gets second circuit in the top link and the first link on the right link. So here is the second link and here is the first link. Now we are in circuit switching, we are dedicating these lines, these resources to this call. So there is no sharing. This line, this connection is only used by these two hosts or end systems. So it's like circuit-like, and we have a guaranteed performance in circuit switching. Circuit segment is idle if not used by call. So there's no sharing. So if, let's say, when these hosts are not talking or they're not video chatting, but they are still continuing the communication, this line cannot be used by others, such as this host. So this host cannot use circuit 1 or link 1 over here. These are only dedicated to these two hosts. Now, this is commonly used in traditional telephone networking, and that's why it's called circuit switching, because in the old days, these devices were actually circuits. So if in the movies, you may remember that there is a telephone operator and she has jacks in her end, let's say, and then she's switching calls, one call from another, and she's inserting jacks into a telephone network. So that's like that. So those lines are only dedicated for this particular call. And of course, the downside for it is that this can only be used for this particular cause. It cannot be used by other hosts, so there's no sharing. But with packet switching, we have sharing, so that the same line or the same connection may be used by multiple hosts, enabling better utilization. But packet switching may have differences or degradation in performance due to the load on the network. But in circuit switching, since we have a dedicated line, we are not sharing that line or those connections, so we have a guaranteed performance. So that's the benefit of circuit switching. But the downside is that it cannot be shared, so we can only have a limited number of connections in circuit switch networks. To have a better utilization in circuit switching, we have two mechanisms called FDM and TDM. FDM corresponds to frequency division multiplexing, and in optical networks, for example, we have electromagnetic frequencies divided into frequency bands. And in this graph, we have a certain band of frequency, and we have time. And we are going to divide this frequency band into 4 users. And these are the colors for each user. Since we have 4 users, we are going to divide the frequency band into 4. So each call is allocated its own band and can now transmit at max rate of that narrow band. So actually, we have a little bit limitation due to the band frequency. So the first user gets this band, the second user gets this band, the user with the orange coloring get this band, and then we have this band for the fourth user. And in time division multiplexing, in TDM, time is divided into slots. So we divided the time into slots rather than the frequency band, and each call is allocated periodic slots. So we can transmit at the maximum rate of the frequency band, but only during its time slots. Okay, so let's say that the first user gets this time slot, and the second user gets this time slot, and the third user gets this one, and the fourth user gets this one. So the first user has to wait its turn until its time slot is allowed for this. Now the advantage of time division multiplexing compared to frequency division multiplexing is that the call can use the maximum frequency band, so it can achieve higher frequencies or have a wider band, but it's limited in terms of time. But with frequency, we may have less frequency band allocated to each line, but then we have the full time, so we don't have to wait for a turn. So this may limit our bandwidth in terms of sending packets, and this we are limited to a certain time slot. So depending on the type of communication, we may use FDM or TDM, frequency division multiplexing, or time division multiplexing. If our conversation is not very much congested, and then there are breaks between our conversation, we may use time division multiplexing. But if we do not need send a whole band of information, but we want to have a constant link, so we don't want to wait our turn, then we may use frequency division multiplexing. Let's take a look at packet switching versus circuit switching. Now here's an example. We have end users connected to one router, and then we have an outgoing link that has a capacity of 1 gigabits per second. Now each user has 100 megabits per second data when active, and then they are active actually only 10% of the time. So how many users can use this network under circuit switching and packet switching? So with circuit switching, well, the solution is kind of easy because each user needs 100 megabits per second when they are active. So we have a link of 1 gigabit per second. So when we divide this link by the need of the users, we will see that only 10 users can use this link efficiently without a problem. But with packet switching, remember that our users are not active all the time. So they're only active 10% of the time. They have only data to send at 10% of the time, but 90% of the time they don't have any data to send. So with this use in mind, we can have more users than circuit switching. And when we calculate it with 35 users, we can achieve that the probability of more than 10 users active at the same time is less than 0.0004. So it's very unlikely that more than 10 users will be active. So assuming that we may achieve more utilization than circuit switching. So how did we get the value of 0.0004? Well, this is a homework exercise for those with a course in probability. Basically, you have to calculate the probability of one user active, and then you have to multiply it by the probability of not having other active users. So when you calculate it, you will see that the likelihood of having more than 10 users active at the same time is quite small. So basically, with packet switching, we can achieve much more utilization, assuming that the users are not active 100% of the time. So based on the example we just discussed, is packet switching a slam dunk winner? Well, it may seem so, but it's only when we have burst data, meaning that we sometimes have data to send, but at most other times we do not. So packet switching is great for resource sharing, and it's also simpler in terms of we don't need a call setup, unlike circuit switching. Now in circuit switching, we need to have a setup mechanism to create the link between two hosts. So that's called call setup. So we need mechanisms for that. But in packet switching, there's also the possibility of having excessive congestion. So because of that, we may have packet delays and packet loss due to buffer overflow, and therefore we need protocols for reliable data transfer and for congestion control. Now, TCP, the Transmission Control Protocol, helps with that, and there are some other protocols where we can achieve or where we can overcome certain problems related to congestion. So, is it possible to provide circuit-like behavior with packet switching? Well, it's possible, but it's also a little bit complicated, and we are going to study various mechanisms that we can try to make packet switching act like circuit switching. And we have protocols for that as well. We learned that the internet is actually a network of networks. Hosts such as our smartphones or such as our laptops or end systems are connected to the internet via internet service providers. Now let's consider that you want to play a video game with a friend that's located in some other part of the world, and so that your gaming applications need to exchange packets with each other so that your ISP router need to be connected to other ISP routers in some other part of the world in some way, and then the resulting network is quite complex, and this evolution is actually driven by economics and national policies, and not in all parts of the world the national policies are the same. In some countries, they may have a more liberal policies in terms of internet use. In some other countries, they may have a more restricted use of internet, so that the resulting network may are actually affected by these various policies. Now let's take a stepwise approach to describe the current internet structure. Considering that we have millions of access networks, how are we going to connect them together? Well, one solution would be connecting each access ISP to each other directly. But this solution doesn't scale. Well, you may remember this notation from your algorithms course, which is the complexity notation. The number of links from such kind of a mesh connection would be n squared. Well, that's a lot of connections, and it's probably infeasible. Now, another option might be connecting each access network to one global transmit ISP. Now, the customer and provider ISP may have an economic agreement, and if this one global ISP is a viable business, then there'll be competitors. And they will also want to be connected to each other, because one host in one access network would like to connect to another host in another access network which belongs to another ISP. So these ISPs need to be connected to each other in some way, and we have internet exchange points for that over here and over here. This internet exchange point is actually connecting ISP A to ISP B, and this internet exchange point is connecting ISP ABC, and sometimes the ISPs have special agreements between each other, and they may have peering links to one of their routers. And we may have regional networks that may arise the need to connect access networks to ISPs. And we may also have content provider networks such as Google, Microsoft, Akamai may run their own network to bring services and content close to end users. At the center of the internet structure, we have a small number of well-connected large networks. These are called Tier 1 ISPs, and these Tier 1 commercial ISPs, such as Sprint, AT&T, have national and international coverage, and these ISPs are connected to each other through internet exchange points. Over here, this internet exchange point is connecting Tier 1 ISP to Google content provider networks. So Google and Facebook, they may run their own private network that connects its data centers to the internet and often bypassing Tier 1 or regional ISPs. Now we have regional ISPs that are connected to Tier 1, one of the Tier 1 ISPs, or they may be connected through internet exchange points to various other content providers or another Tier 1 ISP. And of course, we have access networks that are connected to either directly Tier 1 ISPs, or they may be connected to regional ISPs, which are connected to Tier 1 ISPs or internet exchange points. And we may have content providers that are directly connecting to access networks. And this is a general overview of hierarchical overview of internet structure. Now we are going to talk about performance related issues in networks such as loss, delay, and throughput. So how the packet delay and packet loss occur? Well, the packets queue in router buffers waiting for their turn for transmission. Now the queue length grows when the arrival rate to link temporarily exceeds output link capacity. Well, why is it temporarily? Because if we know for sure that the packets will arrive faster than it's going to send, then we have a deficient network design. But when does this occur temporarily? Well, that depends on the number of hosts that are connected to the router and the applications that are running, the network applications that are running on each host and their communication needs. So the packet loss occurs when memory to hold queued packets fill up. So the packet loss, here is the packet that's being transmitted, which is subject to transmission delay. And here are the packets in buffer. So they are subjected to queue delay. And these are the free available buffers for the incoming packets. So when the arriving packets will be lost or dropped if there are no free buffers. If these buffers are full and the router cannot send packets fast enough, then the new incoming packets will be lost or will be dropped due to not having adequate buffer size. We have four sources of delay causing the overall packet delay. Now, this is our network structure, and we have two hosts such as A and B. These are connected to one router, and now this router is connected to another router, and then these hosts are running networking applications, and these networking applications are sending messages. Of course, these hosts are dividing these messages into packets, and this packet coming from A is colored blue, this packet coming from B is colored blue, green, and then these are queued at the router. Now we have the transmission delay, we have the propagation delay, we have the queuing delay, and we have the nodal processing delay. Now the total delay is actually the sum of all these delays. And now let's take a look at each delay in detail. Now we have nodal processing delay. The nodal processing delay is about the error checking. When these packets are arrived at the router, they are checked for errors, bit errors such as CRC, error control. And remember that we talk about the various mechanisms of routers such as forwarding and routing. Now for forwarding, we have the forwarding tables, and in those tables, depending on the packet destination address, the router is responsible for choosing the required output link. So there is determining the output link, which takes some time, some processing time, and that contributes to nodal processing. Now, in this particular example, we may see that this delay may be in less than microseconds, but of course, as technology progresses, we may have better rates, better processing times in depending on the router technology. Now we have the queuing delay. The queuing delay is about the time waiting at the output link for the transmission, and also that depends on the congestion level of the router. Now, when we have many hosts that are connected to our router, of course, this router has to get all these packets and put them into buffer, so they need to be processed, put into the proper place, and then they should be ready for propagation. So that takes time, and then the queuing delay also depends on the number of hosts that are connected to each other and the number of packets that this router is receiving. Now we have the transmission delay. We talked about the transmission delay in the previous slides. The transmission delay formula is L over R. L is the number of bits in terms of packet length, and R is the link transmission rate, and that's bits per second. Now we have the propagation delay. The propagation delay is D over S. D is the length of the physical link, and S is the propagation speed. Now this is basically distance over speed. So the propagation delay is actually for the packet to travel on this wire, and which is occurring at the light speed. So this propagation delay increases as the physical distance between these two routers increases. Now, this may seem similar to many, but they are actually very different concepts. The transmission delay is about being able to put the packet onto the link, while the propagation delay is about being able to send the whole packet over the wire. Let's take a look at the concept of delay with a caravan analogy. Now, these are toll booths, and these are cars, and these are other toll booths. So these may be like packets that in our network, and these may be our routers. Now, these cars are bits, so they are pieces of information, and the caravan is the packet. So in this particular example, we have a 10-car caravan, also known as 10-bit packets, and then these toll servers, which is the link transmission. So there is the toll booth, also may be considered as the link. Now the toll booth takes 12 seconds to service each car. So that's the bit transmission rate, and the propagation, then each car propagate at 100 kilometers per hour. So each car goes with a speed of 100 kilometers per hour. So the question is, how long until this caravan, 10-car caravan, is lined up before the second booth? Okay, so time to push the entire caravan through the toll booth onto the highway is 12 times 10, right? Each car takes 12 seconds, and then there are 10 cars, so the total processing time in this toll booth for this caravan is 120 seconds, actually 2 minutes. Now, time for last car to propagate from first spool to second spool actually takes about an hour, because each car is going with a speed of 100 kilometers per hour, and the distance is 100 kilometers. So if we divide the distance over speed, then we are going to reach the result for 1 hour. So the total time for processing is 62 minutes. So 2 minutes is coming from 120 seconds, which is the time to push the entire caravan through the toll booth, meaning that the packet processing in the router, and then we have 100 kilometers with cars that are going with 100 kilometers per hour. So the propagation takes 1 hour. So the total time for processing is actually 62 minutes. Now let's modify the example a little bit. We still have 10 cars and we still have booths. And the distance between toll booths is 100 kilometers. Now, suppose that cars now propagate at 1000 kilometers per hour. Now we have race cars and they are going at 1000 kilometers per hour. And suppose that the toll booth now takes 1 minute to service a car. So will cars arrive to second booth before all cars service at the first booth? Well, here is 100 kilometers. If our cars have a speed of 1000 kilometers per hour, this means that they will cover this distance 1/10 of an hour, which is around 6 minutes. So the first car with the service over here with 1 minute will reach the second booth in 7 minutes, right? It will cover this distance in 6 minutes, and there is 1 minute in this processing in this toll booth. So with the first call will arrive after 7 minutes, and then this in 7 minutes, all these 7 cars will be processed through this booth, but we still have 3 cars that are waiting to be processed at this toll booth. So 3 cars still at the first booth. Now, this shows the importance of the propagation when the propagation is much more higher than the processing, then the queue will occur. Let's take a closer look at the packet queuing delay. We have average packet arrival rate A, we have packet lengths in bits L, and we have R, the link bandwidth or bit transmission rate. Now, L times A is the arrival rate of bits, and we have R, which is the service rate of bits. Now, when we divide the arrival rate of bits to service rate of this, we will acquire the traffic intensity. So when we take a closer look at the effects of traffic intensity, if the traffic intensity LA over R is closer to 0, then the average queuing delay is small. So this is what we want to achieve. And when LA over R is closer to 1, then the average queuing delay is large. But when this is much higher than 1, then more work is arriving than it can be serviced. So the average delay is infinite. When we put these into a figure, here is the average queuing delay, and here's the traffic intensity. And when the traffic intensity is close to 1, then as we can see, the average queuing delay goes to infinite. So in terms of a picture, here is what we desire. LA over R is close to 0, meaning that the road is empty, meaning that the traffic intensity is low or close to 0. But here is when LA over R is close to 1, meaning that the traffic intensity is high, and in the picture that we are seeing, there are a lot of cars. So the queue, there will always queue because we cannot service rate of bits enough to clear the road. We talk about delay and loss conceptually, but what the real internet delay and loss look like? Now, the operating system's distributions comes with certain networking utilities, and one of the handy utilities is called the traceroute program. Now, this is Unix and Linux variant. In Windows, we have a similar program, actually the same program with a different name, and in Windows machines, we use the program Tracert. So this program provides real-time delay measurements from source to routers along the end-to-end internet path toward the destination. So I is the router, and for all eyes, for all routers, our computer sends 3 packets that will reach router I on path towards the destination with time to leave field value of I we are going to learn about this TTL, time to leave value. And basically in this with this program, we are trying to measure the round trip time, or in other words, RTT. Now the router I will return packets to the sender. So here's my computer that's running the traceroute or traceroute program, and it's sending, and here's the destination that we want to reach, and we probe this address. We want to probe all the routers until this destination address, and first our host machine will send a probe to the nearest router, and then it will send 3 probes so to get a fair reading from this router. And then it will continue getting probes from the routers along the way, and the router I, this router, let's say, will return packets to the sender. Now the sender measures time interval between transmission and reply. So basically looking at the round trip time. So here, when our computer with the using traceroute gets the measurements from this first router, then it will send 3 probes to the second router, and then it will measure the time between transmission and reply. And then this will continue until it will reach to the destination. Now, when we run a traceroute from the University of Massachusetts to Eurocom in France, and here is the example output from the traceroute program. And also you may do traceroutes from a website called www.traceroute.org, and then there are some different countries that you may initiate the probe from, and you'll see the different trace routes. And here along the way we are seeing, these are the routers, and these are the router names actually in terms of networking. And then for each router, our program sends a probe and gets a response, 3 delay measurement. So in this case, 1 millisecond, 1 millisecond, and 2 millisecond. This is probably the closest router to the machine initiating the traceroute program. And then this is the second router, which is still at the university. And then we are getting similar results because the distances are small, and you can see that the IPs, or we are going to talk about what these are, and the IP numbers are close. We can deduce that this is within the same domain, within the same edu domain. And here again, we are at the same university, University of Massachusetts, and they all have IPs starting 128.119 and 3 in this case, and here this is 240. And the numbers, the delays are still low compared to the delays we are going to see. And now we are going outside the university. How do we know that? Well, the domain name changed, right? These were at umass.edu, but here this is vbns.net, and the IP numbers changed significantly, and the delays increased a little bit more. And here are the 3 delay measurements from Gaia CS umass.edu to CS Gateway CS umass.edu. So there are 3 different delay measurements, and this is again 3 delay measurements from the other router along the way. And when we continue along the router, again, these are all the routers, and we are going to see a jump between the 7th router and the 8th router. Now here we may deduce that, okay, the delay is increased from 22 milliseconds to 106 milliseconds. Well, we can deduce that this is a transoceanic link. So we are changing continents, and remember that this is from a university in US, and we are trying to reach a destination address in France. So we are going to cross the ocean, and this is that link, okay? And then we are seeing other routers along the way until we are still trying to reach our destination, which is Eurocom.France. And you see that there are some stars in routers 17 and 18. This means that these routers are not responding. Now, due to security concerns, routers, uh, some of the routers with high security configurations will not respond to probes from traceroute programs because these may also be used for malicious purposes. So these routers will not send back their name, will not send back if they're alive or not. So we do not actually know what's happening with them. But so we will just get stars without getting any feedback from these routers. But here's the router that we are trying to reach. Here's the domain that we are trying to reach. This is the last router from the host. And then we can see that there are three different measurements, and these are close to 136, so around 130 milliseconds. And here, some kind of different issue is arising between router 11 and 12. In router 12, we see that the delays. Okay, here in router 11, we see that the delay is actually decreasing. So over here, when we look at router 10, this is 114 milliseconds, but here this is 112. So how does that happen? Well, this depends. Remember that the traceroute is doing a real-time measurements, and the congestion, due to the congestion in the network, these times may be different. So when the first probe reaches the router 10, then this router may be congested, so that the round trip time, the delay we get is higher. But when we do a second probe to the 11th router, then the network may be less congested, so that's why we may get a lower measurement. How does packet loss occur? Well, here's our network diagram. We have two hosts, A and B, and here's our router, and we have the buffer. Actually, this is like a waiting area for the packets, and here's the packet that's being transmitted, and here's the packet that's being propagated. Okay, so basically, this buffer, this is actually the memory space in the router, has finite capacity, right? So packets arriving to a fill queue is dropped, actually lost. So here, for example, the packet sent by B, packet arriving to a full buffer is lost because the router will not have does not have enough memory to hold this packet. Then it's going to basically drop this packet, and then it will transmit the packets in its queue. So what happens to lost packets? Well, they're lost. So these lost packets may be retransmitted by a previous node, or by source end system, or even not at all. So sometimes this lost packet may be a problem if it's part of an email, but it may not be a problem if it's like a streaming video, right? If we lose one frame out of many frames, we may catch with our eyes. But if that's a significant portion of an email that includes the address for it, then this packet will not be will we need to be retransmitted to be able to send this email. We talked about delay, we talked about packet loss, and now let's talk about the throughput. Now, the throughput is the rate at which bits are being sent from sender to receiver. So the rate is bits over time, and there are two concepts. One is the instantaneous rate, and the other is the average rate. So the instantaneous rate is the rate at any given point in time, while the average is the rate over a longer period of time. In designing networks, we care about both throughputs because while the average gives us a certain average over time, we sometimes need to be sure that our networks is working without a problem even if we have high instantaneous rates, yeah, and we want to make sure that we are not losing many packets. So here is an example. We have a server with a file of F bits to send to the client, and the link between the server and the router has a link capacity of rs bits over second, and we have another link to the receiver, and we have the link capacity of rc bits over second. Now we may think the throughput like a pipe, like these are like pipes that are carrying fluids. So the server sends bits into the pipe, sends fluid into the pipe. Now in this case, we have a smaller pipe while we have a larger pipe, right? So the pipe that can carry fluid at rate Rs is smaller than the pipe that can carry fluid at rate Rc. So this pipe is bigger, this pipe is smaller, and let's see what happens. So what's the average end-to-end throughput? Well, in this case, assuming that Rs is smaller than Rc, now the throughput will be the smallest of one of these, and since Rs is the smaller pipe, then the throughput we can achieve will be Rs. So what happens when Rs is bigger than Rc? Well, this is actually similar to the first case. The throughput that we can achieve is the smallest of them, and which is Rc. So we will be able to achieve a throughput which is equal to the Rc. Now, link on an end-to-end path that contains the end-to-end throughput is called the bottleneck link. Basically, the link with the smallest capacity is the bottleneck link. So that's the definition of bottleneck link. Now here is a network scenario, and let's assume that we have 10 servers. Right now we're seeing 3, but let's assume that we have 10, and let's assume that we have 10 hosts. Now these servers are sending files to these hosts, and assuming that these are like dedicated links between servers to a link that has a capacity of R. So this Rs is like we are right now thinking, for the sake of the example, this is a dedicated link, this is a dedicated link, and all these links are dedicated, so to supply the example. But let's assume that again this R, this link with capacity R is shared fairly among these 10 servers and client. So each connection gets a capacity of R over 10, right? Per connection end-to-end throughput is R point. Now, so what's the throughput? Well, the throughput will be the minimum of RC, RS, and R over 10, okay? So the capacity that the throughput we can reach from, let's say, this server to this host is the smallest of these 3 links. So there's one link over here, there's another link over here, which is a capacity of R over 10, actually R over N, but in this case we have 10 servers, so this is R over 10, and then we have a capacity of R over RC. So the smallest capacity will determine the throughput for this link, and these are the same for all other connections. Well, in practice, RC or RS is often the bottleneck. Now, the capacity that are at the network core is much bigger than the capacity we can see at the network edge. So we can assume in most cases that this R over N is much higher than the capacity that we are going to see in terms of RS or RC. So basically the throughput we are going to see is either RC or RS, which one is the smallest one, and that's the capacity that we are going to get. That's the throughput that we are going to get. In this lecture, we talk about the network core and we talk about the differences between packet and circuit switching. In packet switching, we talk about store and forwarding and queuing mechanisms, as well as forwarding and routing. And in circuit switching, we talk about frequency division multiplexing and time division multiplexing. Then we take a look at the internet structure. We investigate various types of connections, which one is feasible, and then we see that there are tier 1 ISPs and there are regional ISPs, and they are connected to each other through internet exchange points. And then we talk about certain issues related to performance. We take a look at the source of delay, and we investigated how they're affecting the overall delay. And we talk about how packet loss occurs, and we take a look at the queuing mechanism. And then to understand the performance that we can achieve in connected networks, we take a look at the throughput, and we understand that the throughput is basically determined by the capacity in the chain of connections that has the lowest capacity. So that's the determining capacity throughput that we can achieve in a connected network.